Good morning, everyone. Today we are going to study the important topics from Unit 3 AC to DC bridges and instrumentation amplifiers, that is Kirchhoff's law, Flintstone bridge, and Kelvin double bridge. These concepts are very useful in electrical measurements, especially for accurate resistance measurement. First, we will revise Kirchhoff's laws and then move to bridge circuits. Now we will study Kirchhoff's current law, also called KCL. This law states that the algebraic sum of currents meeting at any junction in a circuit is zero. Whereas the total current entering a junction is equal to the total current leaving that junction. By convention, we take the current flowing towards the junction as positive and the current flowing away from the junction as negative. So mathematically, it can be written as I1 plus I2 plus the minus I3 plus I4 plus I4 equal to 0. We can rearranging this equation, we get I1 plus I2 plus I4 plus I3 equal to I5 equal to I3. This means that the sum of currents entering the junction is equal to the sum of currents leaving the junction. In the diagram shown, several currents meet at a single node. Some currents are entering the node and some are leaving from the node. According to Kirchhoff's current law, the total of all incoming currents must be equal to the total of all outgoing currents. This law is based on the principle of conversion of charge, which states that electric charge cannot be created or destroyed. Therefore, the charge cannot accumulate at a junction and hence the current entering must equal the current leaving. Kirchhoff's current law is very useful for solving complex circuits using nodal analysis. Now we will study Kirchhoff's voltage law, also called as KVL. This law states that the algebraic sum of all voltages around any closed loop in a circuit is zero. In mathematical form, it is written as sigma V is equal to zero, or V1 plus V2 plus V3 and so on up to Vn equals to 0. This means that the sum of voltage rises in a loop is equal to the sum of voltage drops in the same loop. This law is based on the principle of conversion of energy, which means the energy is neither created nor destroyed, but only converted from one form to another. Now let us consider the closed loop shown in the diagram, that is the path A, B, C, D, E, F, and A. Along this closed path, current flows through different resistors and sources. Each resistor causes a voltage drop equal to current multiplied by resistance. That is I into R. Each battery or source provides a voltage rise equal to its EMF value. Applying Kirchhoff's voltage law to this loop, the sum of all voltage drops across resistors is equated to the sum of the source voltages. Similarly, for another closed path A, B, E, F, A, we can again apply Kirchhoff's voltage law and write a loop equation by adding all voltage drops and equating them to the algebraic sum of the EMFs. So by selecting different closed loops in a network and applying KVL, we can form equations which can be solved to find unknown currents and voltages. Thus, Kirchhoff's voltage law is very useful for loop analysis and mesh analysis in complex electrical circuits. Now we will study the Wheatstone bridge. The Wheatstone bridge is also called a resistance bridge because it is mainly used to measure an unknown electrical resistance accurately. This bridge is a practical application of Kirchhoff's laws in electrical circuits. It helps us determine an unknown resistance by comparing it with known resistance. This circuit consists of four resistors arranged in a form of a bridge. Out of these four resistors, two resistors have known values, one resistor has an unknown value, and one resistor is a variable resistor. All these resistors are connected in a diamond or bridge shape. A galvanometer is connected between the middle points of the bridge, and a DC source is connected across the outer terminals. When current flows through the circuit, the variable resistance is adjusted until the galvanometer shows zero reflection. This condition is called the balance condition of the Wheatstone bridge. At balanced condition, no current flows through the galvanometer. This means the potential difference across the galvanometer is zero. At this point, the ratio of resistance in one arm is equal to the ratio of resistance in the opposite arm. So we can write P by Q is equal to R by S. Using this relation, the unknown resistance can be calculated accurately. Wheatstone bridge is very reliable and gives accurate results because at balanced condition, the galvanometer resistance does not affect the measurement and there is no power loss in the galvanometer branch. Hence, the Wheatstone bridge is widely used for phase resistance measurement and in sensor-based applications such as strain gauges and in temperature measurement. In this diagram, the four resistors form four arms of the bridge. The unknown resistance is placed in one arm. Galvanometer is connected between the two midpoints. A DC source is connected across the bridge. By adjusting the variable resistor, we bring the bridge balance condition. Let's understand what happens when a Wheatstone bridge is in balanced condition. The Wheatstone bridge consists of four resistors arranged in a diamond shape with a galvanometer connected between the middle points. Now, when we say the bridge is balanced, it means no current flows through the galvanometer. So the galvanometer reading becomes zero. Why does this happen? At balance, the electrical potential at both midpoints of the bridge becomes the same. Since current flowing only flows when there is a voltage difference, equal potential means no current passes through the meter. In this condition, the current flowing through one of the resistors equals the current in its corresponding lower resistor. So we can say current through R1 equals current through R3 and current through R2 equals current through R4. Because, because of this, the voltage drop across corresponding arms are proportional. This gives the balance condition R1 by R2 equal to R3 by R4. So the ratio of resistance in one branch equals the ratio in the other branch. When this relationship is satisfied, the bridge reaches equilibrium, the galvanometer shows zero deflection, and the circuit is perfectly balanced. This principle is mainly used to measure an unknown resistance very accurately. In this Wheatstone bridge circuit, four resistors are connected in a diamond shape. Here, R1 and R2 are called the ratio arms. R3 is a known resistance. Rx is the unknown resistance that we want to find, and a galvanometer is connected between points A and B. When the bridge is adjusted to balance condition, the galvanometer shows zero deflection, meaning no current flows through it. At balance, the potential at points A becomes equal to the potential at point B. Therefore, current through the galvanometer is zero. Now, applying Ohm's law to both sides of the bridge, the voltage drop across the left branch gives I1 R3 equal to I2 Rx, and the upper branch I1 into R1 equal to I2 R2. Dividing these two equations, eliminates current and gives R3 by R1 equal to Rx by R2. Rearranging the equation, we obtain the unknown resistance. Rx equal to R2 by R1 into R3. So by knowing R1, R2 and R3, we can accurately calculate the unknown resistance Rx. This is why the Wheatstone bridge is widely used for precise resistance measurement. Now let us know the applications. The Wheatstone bridge is used to measure low resistance accurately by using sensors like thermistors and strain gauges. We can measure temperature, light intensity, and strain. Modified Wheatstone bridges are also used to measure inductance, capacitance, and impedance in AC circuits. One major advantages of Wavestone bridges is that at a balanced condition, no current flows through the galvanometer. So the galvanometer resistance does not affect the result. Also, there is no power loss in the galvanometer branch. This gives high accuracy and reliability. The drawbacks of the Wheatstone bridge is it is not suitable for measuring very high resistance because galvanometer deflection becomes very small. Also, heating of resistors due to current can change their resistance values. This leads to errors and reduces accuracy. Now, let us move on to the Kelvin double bridge. The Kelvin double bridge is an improved form of Wheatstone bridge used to measure very low resistance. It is used to measure contact resistance, cable resistance, shunt resistance, and armature winding resistance. Ordinary Wheatstone bridge is not suitable for very low resistances due to lead resistance error. When we measure very low resistance, the resistance of connecting leads and contacts becomes comparable to the unknown resistance. These unwanted resistance introduce large error in Wheatstone bridge. Kelvin double bridge eliminates this error by using an additional set of ratio arms. Now let us understand the construction of the Kelvin double bridge. The Kelvin double bridge is a modified form of the Wheatstone bridge, mainly used for measuring very low resistances accurately. In this circuit, we have two main ratio arms R1 and R2, a known standard resistance R3, and an unknown low resistance RX. A galvanometer is connected between points A and C, and an additional set of ratio arms called A and P. The important feature of the Kelvin double bridge is this second set of ratio arms, labeled small a and small b. These arms connect the galvanometer to a point C, which lies between points M and N. This arrangement helps eliminate errors caused by lead resistance or contact resistance, which becomes significant when measuring very small resistance. For proper operation, the ratio of resistance in ohms A and B is made equal to the ratio of R1 and R2. When this condition is satisfied, the potential at point A becomes equal to the potential at point C. As a result, no current flows through the galvanometer. Hence, the bridge reaches the balanced condition. This special construction allows the Kelvin double bridge to provide highly accurate measurement for low resistance. The construction of the Kelvin double bridge is similar to the Wheatstone bridge, but it includes two additional set of ratio arms. These arms are P and Q. It is the main ratio arms. Small p and q, the auxiliary ratio arms. In this arrangement, the arms P and Q are connected to one end of the galvanometer at point D. These arms P and Q are connected to the other end of the galvanometer at point P. The unknown resistance R and the standard resistance S are placed between points A, M and N, C respectively. The purpose of adding these extra ratio arms is to eliminate errors caused by connecting leads and contact Excuse me. which are very significant when measuring low resistance. For accurate measurement, the ratio of the axillary arms is adjusted such that P and P by Q equal to capital B by Q. When this condition is satisfied, excuse me. When this condition is satisfied and the bridge is balanced, no current flows through the galvanometer. The potentials at the galvanometer connection points become equal. At balance, the voltage difference between points A and B becomes proportional to the voltage drop along the measured resistance path. This allows the effect of lead resistance R to be cancelled, giving a highly precise value of the unknown resistance. Hence, the Kelvin double bridge provides accurate measurement of very low resistance by minimizing measurement errors. Now let us understand the balance condition and final equation of the Kelvin double bridge. When the bridge is adjusted properly, the galvanometer shows zero deflection. This means no current flows through the galvanometer, indicating that the bridge is balanced. At this balanced condition, the potential difference across the both galvanometer terminals becomes equal. By applying circuit analysis and voltage division in the bridge network, we obtain an equation relating the unknown resistance R, the standard resistance S, the ratio arms P and Q, and the auxiliary ratio arms small p and q, including lead resistance effects. Initially, the expression for resistance contains an additional term due to lead resistance R. However, in Kelvin double bridge operation, we make an important adjustment. Capital P by Q equal to small p by Q. That means the ratio of the main arms is made equal to the ratio of the auxiliary arms. Because of this condition, the error term caused by lead resistance gets cancelled. So the equation simplifies to the final balance condition R equal to P by Q into S. This shows that the unknown resistance R depends only on the known standard resistance S and the ratio of arms P and Q. Hence, the Kelvin double bridge provides very accurate measurement of low resistance independent of lead contact resistance. Next, we will see about the advantages of Kelvin bridge. The Kelvin double bridge has high sensitivity and high accuracy. It can measure very small resistance values. Power consumption is very less and construction is simple. It is widely used for low resistance measurements. Next, the disadvantages of Kelvin double bridge. A sensitive galvanometer is required to detect balance conditions. High current is needed for good sensitivity, and a manual adjustment is required, which makes measurement time consuming. This brings us to the end of the presentation on Kirchhoff's laws, Wheatstone bridge, and Kelvin double bridge. Thank you for your attention.